The Lemke-Howson algorithm. Algorithms 3.4 and 3.5 find all Nash equilibria of a non-degenerate bimatrix game AB. In contrast, the Lemke-Howson for a short LH algorithm finds one Nash equilibrium and provides an elementary proof that Nash equilibria exist. The LH algorithm follows a path called LH path of vertex pairs xy of P cross product Q for the polytopes P and Q defined in a 3.6 that starts at 0, 0 and ends at a Nash equilibrium. An LH path alternately follows edges of P and Q, keeping the vertex in the other polytope fixed. Because the game is non-degenerate, a vertex of P is given by n labels, and the vertex of Q is given by n labels, and edge of P is defined by n-1 labels. For example, in figure 3.2, the edge defined by labels 1 and 3 joins the vertices 0 and C. Dropping a label L of a vertex X of P, say, means traversing the unique edge that has all the labels of X except for L. For example, dropping label 2 of the vertex 0 of P in figure 3.2 gives the edge defined by labels 1 and 3 that joins 0 to vertex C. The endpoint of the edge has a new label, which is set to be picked up. So, in the example, label 5 is picked up at vertex C. The LH algorithm starts from 0, 0 in a P cross product Q. This is called the artificial equilibrium, which is a completely labeled vertex pair because every pure strategy has probability 0. It does not represent a Nash equilibrium of the game because the 0 vector cannot be rescaled to a mixed strategy vector. An initial free choice of the LH algorithm is a pure strategy K of a player. Any label in M union N called the missing label. Starting with xy equals to 0, 0, label K is dropped at the endpoint of the corresponding edge of P if K is in M, of Q if K is in N. The new label that is picked up is a duplicate because it was present in the other polytope. That duplicate label is then dropping in the other polytope, picking up a new label. If the newly picked label is the missing label, the algorithm terminates and has found a Nash equilibrium. Otherwise, the algorithm repeats by dropping the duplicate label in the other polytope and continues in this fashion. In the example 3.3, suppose that the missing label is K equals to 2. The polytopes P and Q are shown in figure 3.2. Starting from 0 in P, label 2 is dropped, traversing the edge from 0 to vertex C, which is the set of points X of P that have labels 1 and 3, shown by an arrow in figure 3.2. The endpoint C of that edge has label 5, which is picked up at the vertex pair C0 of P cross product Q. All labels except for the missing label 2 are present. So label 5 is now duplicate because it is both a label of C and of 0. The next step is therefore to drop the duplicate label 5 in Q, traversing the edge from 0 to vertex P while keeping C in P fixed. The label that is picked up at vertex P is 3, which is now duplicate. Dropping label 3 in P defines a unique edge defined by labels 1 and 5, which joins vertex C to vertex D. At vertex D, label 4 is picked up. Dropping label 4 in Q means traversing the edge of Q from P to Q. At vertex Q, label 2 is picked up. Because 2 is the missing label, the current vertex pair DQ is completely labeled and it is the Nash equilibrium found by the algorithm. In terms of the game, the first two LH steps amount to taking a pure strategy given by the missing label K, say of player 1, and considering its best response, say J, which defines a pure strategy pair Kj. If this is not already an equilibrium, the best response I to J is not K, so that I is a duplicate label and is not given positive probability in addition to K. In general, one possibility is that a duplicate label is a new best response which in the next step gets positive probability as in this case. Alternatively, the duplicate label is a pure strategy whose probability has just become zero so that it no longer needs to be maintained as a best response in the other polytope and the path moves away from the best response. Face it. Algorithm 3.6 Lemke Howson. Input non-degenerate bimatrix game. Output 1 Nash equilibrium of method. Choose K in the union of M and N. Call the missing label. Let xy equals to 0, 0, a pair of zero vectors in a P cross product Q. Drop label K from X in P if K is in M, from Y in Q if K is in N. Loop. Call the new vertex pair XY. Let L be the label that is picked up. If L equals to K, terminate with Nash equilibrium XY, rescaled as mixed strategy pair. Otherwise, drop L in the other polytope and repeat. The LH algorithm terminates and finds a Nash equilibrium because P cross product Q has only finitely many vertex pairs. The next vertex pair on the path is always unique. Hence, a given vertex pair cannot be visited because that would provide an additional possibility to proceed in the first place. We have described the LH path for missing label K by means of alternating edges between two polytopes. In fact, it is a path on the product polytope P cross product Q given by the set of pairs XY of a P cross product Q that are K almost completely labeled, meaning that every label in M union N minus the set of K appears as a label of either X or Y. In figure 3.2, for K equals to 2, the vertex pairs on the path are 0, 0, C0, CP, DP, and DQ. For a fixed missing label K, the K almost completely labeled vertices and edges of the product polytope P cross product Q form a graph of degree 1 or 2. Clearly, such a graph consists of disjoints, paths, and cycles. The endpoints of the paths are completely labeled. They are the Nash equilibrium of the game and the artificial equilibrium 0, 0. Since the number of endpoints of the paths is even, we obtain the following. Corollary 3.7. A non-degenerate bimatrix game has an odd number of Nash equilibria. The LH algorithm can start at any Nash equilibrium, not just the artificial equilibrium. In figure 3.2 with the missing label 2, starting the algorithm at the Nash equilibrium, DQ will just generate the non-LH path backward to 0, 0. When starting at the Nash equilibrium AS, the LH path for the missing label 2 gives the vertex pair BS, where label 5 is duplicate and then the equilibrium BR. This path cannot go back to 0, 0 because the path leading to 0, 0 starts at DQ. This gives the three Nash equilibria of the game as endpoints of the two LH paths for missing label 2. These three equilibria can also be found by the LH algorithm by varying the missing label. For example, the LH path for missing label 1 in figure 3.2 leads to AS. from which BR is subsequently found via missing label 2. However, some Nash equilibria can remain elusive to the LH algorithm. An example is following symmetric 3 by 3 game, which with A equals to B transpose equals to the following: 330, 401, 045. Every Nash equilibrium xy of this game is symmetric, i.e. x equals to y, where x transpose is 001, 1 half, 1/4, 1/4, or 3/4, 1/4, 0. Only the first of these is found by the LH algorithm for any missing label. Because the game is symmetric, it suffices to consider the missing labels 1, 2, 3. A symmetric game remains unchanged when the players are exchanged. A symmetric game has always a symmetric equilibrium, but may also have non-symmetric equilibria, which obviously come in pairs.